Hello, hi everybody, and welcome. I hope you're going to enjoy this afternoon. Some of you know what happens next very well, and some of you perhaps are new to this idea. So I'll go very, very quickly through these first few slides from the PowerPoint, just to give you a flavour of what we're about. Some of us have been doing what happens next ideas for quite some time. You see on that first slide, 2010 to 2023, I've been putting things in physics education. And then since lockdown, we've had what happens next pages on Facebook. But it began with the problem of how to engage, how to get you motivated and get your students really engaged, and it applies to all ages. How to involve your students in scientific thinking and discussion. Sometimes we only really involve in the lessons and in the thinking a small number of students in our class. And we found that this approach, however you do it, can just about involve everybody. We just click on, please. So the solution that we came up with was to have short demonstrations in a format that lent themselves to discussion. Not just sort of do this, do that, and here are the results, but have something that made people think, and particularly in a non-threatening environment. Next. So we came up with this strategy. It's interactive, it involves people, it helps develop thinking skills, it aids group activity and so on, it helps insight, explores misconceptions, and it's fun. It's great fun to sometimes get things wrong and then get them right again, or work out just what's happening and find something as well that you can do at home. You can take the ideas home. Next. So you could use this in lots of ways. It's not a sort of standard way that everybody will do. Simple questions just to reinforce knowledge. Using apparatus perhaps that they don't normally use. Well, that checks whether you understand what you did in the lab. Probing questions for less known areas of STEM. Now, you've got to be a little bit careful that you don't put students off. And certainly if you do a what happens next selection, always start with nice, easy questions that people can get right, rather than start with the difficult ones. They might be appealing to you, but they're not necessarily appealing to the students. And remember, if you're teaching science or you're teaching physics or maths, you were probably good at science and physics, at maths, whereas the majority of your students aren't as good as you. And so that's the, out of 30, perhaps there's 5 people that are sort of at your level of ability and the rest are a bit below. So don't put them off. We can examine understanding when the outcome's not expected as expected. And also very important, test observation skills, especially when the outcome is not as expected. The older students will have theories as to why things happen. Younger students, particularly the primary students, it's more about observing things carefully. Okay, move on. So you can use this simple starter, beginning and end of a lesson. You can use it even to assess whether they've got the ideas that you've been teaching. For me, it began as an end-of-term quiz activity. What I like very much is seeing the students themselves demonstrate these ideas at an outreach or parents meeting. I know of, or my son has used some of these, when he's been interviewing. He's an engineer, he heads up a research company, and when he's trying to assess whether his candidates for a job can think or not, he uses some of these. And it's fun, and it works for all ages and levels. Next, are we nearly at the end of this boring bit? You can check the experiments out in physics education. There's an archive of all the experiments I've had published there since 2010. Facebook page is What Happens Next Experiments, that we started at lockdown, and we've done them every day. There's new ones every day. And then there's previous Science on Stage webinars that you can look through. Okay, I think we're finished with those slides. Oh yes, just a thanks to those who've inspired me over the years with ideas, and hopefully still continue to inspire me, and I hope they'll do with a few ideas. You might come up with a few ideas that we can use in the future. So let's get on and see where this started with some nice little easy experiments. Forgive me if you've seen these before, but what's been happening recently is ideas have come out of the original simple idea. So one of the nice ones that I like, and I like this particularly because some really clever people that I know got it wrong the first time. And don't say, oh, not this one again, because... So what we do, we have two balloons, identical balloons, apart from the fact that they're the same, different colours, and we're going to join the two balloons with this connector tap. You don't need any fancy taps, although these are sort of quite handy. You can just use a freezer clip and a little piece of tubing and stick the balloons on either side, and you've got a way of sealing them. And what happens next when you open the tap? The majority of people immediately say, oh, they'll equalize. We're looking at large size and thinking bigger. Oops, it's just leaking a bit. Let's blow it up again. Biggest is best, because you can use this as an illustration if you be it in a PSA meeting or an assembly or in church. What's the most important? What's most important is what's inside the balloon, not what's on the outside, and it's pressure. So when you open the tap, the little one's blown the big one up. What a surprise. Why is that? Because the pressure in the little balloon is bigger than the big balloon. The pressure in a balloon doesn't go up in a straight graph like that. It starts big and then goes down and then goes up again at the end. Very small children will understand that because it's hardest to blow a balloon up at the beginning. Mummy, will you start the balloon? So the pressure's the thing. So they understand it just from the point of view of being hard to blow up a balloon. It's got more force in. Or you can go further. Zuzana Jaskova in Slovakia has done a lovely article about the pressure in a balloon. You can investigate further. It leads on to further investigation about pressure in a balloon. What happens when it's been up and come down again? It's changed, and so on and so forth and so forth. Another one that leads on from that is you've got two balloons, identical balloons, and you say, right, I want you to blow them both up. Here's a connector, one of these Y connectors. Blow them up. You can't blow them up together because of this variation in pressure. One balloon will always start before the other. Not tried this, but with these balloons, you have new balloons, so just prove it. You see, this one has started, but this one now needs more pressure in order to blow this one up. So it's another illustration that you can do. Just putting these in a bag here, getting them out of the way. As I tripped on the stairs yesterday, and this leg is just killing me. So I can't really move around. So I've got everything labeled up here, ready. So that was the start, and that's what got me going. And the other one that got me going on this was the old Sultanas in lemonade experiment. I hope there's a enough fizz in this lemonade still. Lemonade. Oh yes, there's a bit. And when you put, do you know this one? When you put some Sultanas in, the bubbles form. I think you can see that. Bubbles form on the Sultanas, and they rise and they fall to the bottom. Lovely one to explain, lovely one to observe what's going on. Marvellous. But what about? It's Easter, isn't it? So why don't we do it with some chocolate eggs? Well, first of all, I got some of these sugar sugar-coated eggs. What will happen with a sugar-coated egg, right? Will it be the same? Oops, we need the lemonade. Right, let's see. You can do this with salted peanuts, but it spoils the lemonade for drinking afterwards, whereas Sultanas and these little tiny eggs, and this is interesting. I thought these would go up and down again, but no. Wow, there's a host of tiny bubbles. Did you see that? Tiny bubbles come off. No, not sufficient to raise the sugar-coated sweets. Somebody can tell me what that gas is, whether it's the sugar-coated dissolving, but my theory is because the eggs are so smooth, there's not enough sites to provide larger bubbles. So I get a larger egg. Will a larger egg give larger bubbles? No, exactly the same thing happens, like a cloud of tiny bubbles we can observe. Tiny bubbles you can see, I think, on the Smartie egg. That is a sugar-coated chocolate egg. So, well, what about a chocolate egg? See how you go, this is what a white chocolate. I've never done it with a white chocolate egg. Doesn't seem right to have white chocolate. There you've got bigger eggs, bigger bubbles, but that's not many. I wonder if they I have done this with a chocolate egg, and let's try. This is the real cream egg. Nice chocolate egg. Let's see if it'll catch enough. Put a bit extra fresh. I'll start on a fresh one. So it's not expensive. This was the cheapest lemonade I could find, as you can imagine. Pop that in, and bubbles. There's just not enough bubbles. When I did this the other day, you can see there's a lot of bubbles forming. I wonder if it'll rise. More and more coming. Go on, get up. No, there's not quite enough to lift it off. It lifted off last week when I tried this first. But you can sort of make your experiments sort of Easter friendly. I'll put those down there and hopefully not kick them over. So that was a sort of interesting start. What I would like to sort of suggest is that you have a few of these experiments that are as much observation as they are really deducing what's going on. This is one of it was a lovely one to do with children and get them to understand what's happening. Just to look at the bottle will provide enough discussion as to what's inside. Of course, it's not water. Looks like water, but it's not pure water. This is isopropanol. These beads are sort of, well, I suppose they're special beads from educational innovations. And this is brine. This is salty water at the bottom. The isopropanol and the salty water don't join together. They'll mix up, but they don't actually change. So what happens? And can you describe what's happening all the time? A little press. Give it a good shake. And look at the beads. Now what's going on? Oh my, they were in the middle. Now there's one's at the top, one's at the bottom. But if you look carefully, they're not staying there. Can you see the white beads are falling? So there's something going on in the bottom. That's quite fascinating to watch here. The blue ones are coming up now. Presumably they're going to end up in the middle. We've now got 5 different states there that are quite a challenge for a young person to describe what is going on. We've got the isopropanol at the top that's separated out. We've got the white beads, which are less dense than the isopropanol, but denser than the mixture of water and isopropanol. The blue beads, which are less dense than the brine. Can you see how that would be quite a discussion that you can have? And it's an observations thing. The other observation one I wanted to show you very briefly, this is a coffee saver. You can evacuate it. I've already part evacuated it, and because it's nearly Easter, inside we have Easter bunnies and ducks. No chickens in that, just there you are, there's a nice little bunny. What I put in was marshmallows. Look at the size of the little marshmallow that went in. And I've taken the air out with this pump. I did it before because I can't run around. And sort of, you can start this by saying you can put ordinary marshmallows in. They're bigger, they're probably better for expanding. When you take the air out of the surroundings, the marshmallow expands because the air bubbles inside expand, right? And they don't escape, they stick there. A bit like if you put a small balloon inside a vacuum chamber and evacuate, the balloon will blow up because of the air that's already inside it. So the bubbles are there, they've expanded because the surrounding air is at less pressure, and you can see the size of the little one. If I let the air back in, children always get a bit upset. The girls seem to get upset with this when I do it. The boys don't seem to mind. And they all go back to the small size when the air goes in. So that's a sort of fun. If you've got one of these coffee savers, it's something you can do with that. So you can see we're racing through. We're into Easter. Now here's a good one that will get people going. You know the experiment where you have a bit of paper and a weight and you drop them and the paper falls down gently and the weight goes down like that because of the air resistance. A lot of junior children do air resistance and they think this air resistance is really big. I'd suggest, why not try with two eggs, chocolate eggs, this next few weeks. Now these are interesting because these two eggs are the same inside. So you could say, are they the same? How would you know whether the cream egg small is the same as the cream egg big? Give them a challenge. Just a bit of a blast from the past. Have you got one of these? Eureka can? So you could find the volume and find the mass and find that the density of these two is the same. And therefore you probably conclude that they were the same egg. So what about dropping them? Well, if you drop them together, always be the same person doing the dropping and listen carefully. One bonk at the bottom means that they both drop together. A lot of them will think the big one will drop faster than the little one, but they drop together for quite a distance. Here's it for the older children. How far do they have to fall to reach their terminal velocity? And which one will be going faster once it's reached its terminal velocity? We're not dealing with something that's light and something that's heavy, different materials. We're dealing with the same material. So you can work out using Stokes' law. Remember? I mean, I've got to remember these things. It's years since I taught this. Stokes' law to drop. And when the force equals the downward force equals the upward viscosity force, and that's reached the terminal velocity. Which one will go fastest? Well, first reaction of a lot of people is to say the bigger one has more air resistance. Well, it does, but it's heavier as well. How is it heavier? It's heavier with R cubed, the volume of the egg. Whereas the little one, it's heavier with R cubed, but the air R cubed is small. If it's half the size, remember R cubed, 222 is 8, so it's 8 times less. So then there's another thing you could do with these two eggs. I've dropped one. You could measure them. You could measure them and think, well, how heavy are they both? Is it good value to buy these eggs, big ones or little ones? So if you measure this egg, here's a test for you before the end of the session. That's 5 centimeters from top to bottom. I know it's not spherical, but you can use the length. And this one is 3.25 from top to bottom. Okay? And I know how heavy this is because it says on the packet 5 times 40 grams. So this is 40 grams. I did check. It is 40 grams. Don't believe what you read on the packet. So how heavy is this? 5 centimeters, 3.25 centimeters, 40 grams. There's something to be working on if you get bored with me, but you'll not get bored with me for too long because somebody else will be coming to do some experiments. By the way, we've got a sheet of all the experiments that we've done with clues and so on that you will be able to get after this show. Right, so that takes us on to something else you could do with eggs, which is float them or sinking. And I'm really, really thrilled that Jules Pottle has made a video of this next little experiment.
Hello, so here's a what's happens next for you. I've got an egg, and the first thing I'm going to do is crack it and empty out the and then I've got 2 glasses of water, and I'm going to put the eggshell into the water to see what happens. So I'm going to take my first bit of eggshell and I'm going to fill it with water and let go. It's gone all the way to the bottom. What do you think is going to happen when I do the same with the other part of the egg? Is it going to float at the top, or is it going to sink down to the bottom? What do you think? What happens next? What did you think? What were you expecting to happen? What do you think was going to happen next? Let's try it. So let's pop this one in, fill it with water in just the same way, and let go. Oh. Oh. That one's still at the top, look. All right, I'll try filling it with water. I'll hold it just underneath, look. There we go, and let go. Oh. It's still hanging around at the top. Right, I'm going to really push it down as far as I can go. Oh, it's bobbed back up again. So if we take these 2 eggshells out, you'll see that's the pointy end. And then this is the rounded end, the bottom. Now, if I just hold those up to the camera, you might be able to see in the bottom there, there's a pocket. And it isn't in that one, but this one's got a little pocket that is full of air. And that little pocket full of air is acting a bit like an armband. It's making it float, the air's bringing it back up to the surface. Let's just try it one more time. No, I can't get that one. I can't get it to sink at all. But I'm going to pop the membrane and see what happens. But there's my floaty one. and I'm going to pop them over inside. Right. Hopefully that fit. Let's try it now. Whoa! So, if you want to challenge a friend, crack an egg, give them one half, and say, here you go. You see if you can make yours float like mine, and watch them struggle as they try.
If you're interested in food and eggs, this is the book for you. Bit thick, but it's full of interesting facts about eggs and the air sac and how the air sac grows as the egg gets older, and as it cools down. Floating and sinking is a really good area. You may have seen in previous webinars we've done the orange. The orange sinks, take the peel off, and the inside sinks. No, sorry, start again. Put the orange in and it floats, right? Take the peel off and the inside sinks and the skin acts like a buoyancy. Lots of discussion with that. Or following in Jules' footsteps here, take an orange, cut it in two, get untried this, with this orange anyway. And what will happen when we float this orange? Or you sink it? It will float because it's still got its skin on. But will it float like that? Or will it float like that? You know? Which way do you think? A lot of people will say it will float like this because they're thinking of a boat. But of course the heaviest part is this top part, and the light part, a bit like the air sac, is the top. So when you put it in, see that? Floats upside down. There's a good, what happens next? Right, get rid of that. Now it's up to Rute to inspire us. Hi, Rute.
Yes, hello everyone. Thank you, David, for your so many what happens next that inspire me using it in my lessons. And so today I bring to you Harry Potter. So Harry Potter, to show you an experiment. I'm just going to put it up here. And we're going to put Harry Potter in water. Look very carefully. And looks like Harry Potter has disappeared. We only can see the glasses. So I start my lesson about light with Harry Potter. So when I do this in my lessons, I ask always, what happens next? I have Harry Potter, I will put in water, and what happens? And some of the kids will say, oh, Harry Potter will shrink, will increase in size, or Harry Potter will disappear. But of course, some of the kids will say, Harry Potter gets wet. So this is a nice experiment to do about light, and we can talk about the reflection and the total reflection inside of this bag. So I have here a piece of paper with Harry Potter, and then with permanent marker, I will draw in the plastic bag just the glasses. And when I put in water, it's inside, I can't see. I only can see what it's in the plastic bag, because inside the light will bounce and we can't see what it's inside. We call this total internal reflection. And we can use this with kids and talk about germs and the importance that we should always wash our hands before we go to the table to eat. And so we can use this inside. I have lots of germs that we have in our hands, and I draw a hand in the plastic bag. And of course, you can imagine what will happen when we wash our hands properly. The germs will disappear and our hands are very, very clean. Okay, so this is also a nice one. And also what happens when we add water to a candle? Of course, the flame will disappear. And for the older ones, we can also use a secret message. Oops, let's see if I can do this with the yeah, I don't know if you can see properly, probably the angle, because the trick thing here is just the angle where we can see. So I use a piece of paper, and then I just draw in the plastic bag the letters that I want to appear when I add this to the water. And I think this is an easy, funny, simple way of talk about light and other things in the middle. Thank you.
We should be on the Tissandier experiment now. Or shall I do something in between? Oh, here we are. This is my grandchild.
This is our version of a very famous experiment. So we've got here 2 eggs, and then we've got a thin bit of wood here, and we've got 2 little balls on here. Right, so the question is, what would happen if I was to hit this dead in the centre here? What would happen? Right, so there. So this is the answer. So what would happen when I hit this as hard as I can? The 2 balls here. Where have they gone? One's hit. No, not. It's not. It's all Alan. All right. 2 balls fly up in the air, and the eggs are perfect. No cracks or anything in them, and they are all good. I'm going to try and attempt this same experiment, but the only difference is with bread and tomatoes, and there's a little cut here in the bread because it's very old, and I'm going to hit it with a stick to see if it will work, okay? And Chewy and Charlie here are going to try and catch these tomatoes. If they get them, they get to eat them. I'm sure they'll love that. Ready? You ready, Charlie? You ready, Joey? Yeah? Ready? Steady. Come on. Where did it go? I'm behind you. Oh. Well, the same experiment does work with the French bread. And the tomatoes are still undamaged. That's really good, isn't it?
I hope you enjoyed that. They're all on the worksheet that you're going to get. Some lovely sort of slower motion of the 2 halves of the wood breaking and lifting off the eggs, and you can see the table tennis balls rising up. And just to mention, that experiment is described in the new food and cooking booklet that's just out this week from Science on Stage, Eggs Experiment. I hope you'll all grab that. And there's lots you can do before Easter for that. But here's something that's totally different. Now, another thing you can do with What Happens Next is to introduce something that they've no idea about at all, and maybe even got a wrong concept. So here I've got a grape roundabout, drawing pin, a straw, and 2 grapes, one on either side. The beauty, a really nice little thing about this is it's not quite level there, so we can just pull this grape out a little bit and it will balance. Oops, too far. You can see you can do a little bit with moments. So the question is, what will happen with a neodymium magnet if we hold it beside the grapes? Well, grapes are not magnetic. Well, of course, grapes are slightll magnetic. Grapes are diamagnetic. That's because of the water in them. I'd never heard of diamagnetism until about 3 or 4 years ago when I looked it up and did an article in Physics Education about it. The grapes are diamagnetic, or the water in grapes is done, so it is repelled by a very strong magnet. What happens is there's rearrangements of the electrons within the water, and so when I hold the magnet beside it, you can see not touching, but it's moving away. Right. So that's put paid to one of the theories, school theories of magnetism. What else is magnetic in some ways? Well, if got to get this the right way around. Aluminium, on the other hand, isn't repelled by a magnet. It's attracted by a magnet because it's paramagnetic. So if I hold, this is a Japanese yen, get some Japanese yen, they float on water. Lovely to do surface tension with them. And you can see that's attracted by the magnet very slightly. And so we have this experiment, a roll of, can you see that just, I think, a roll of aluminium, hold the magnet beside it, and the aluminium is attracted to the magnet. You can see I'm moving the aluminium around with the magnet, so it faces the magnet. What will happen if you put, instead of aluminium, we've got a glass rod? What will happen there? I hope your brains are coping with all this and you're managing to think a little bit. Put the glass there. Now, glass is diamagnetic, so it's repelled by a magnet, and so the glass will settle. If you put it by the end is repelled, so it tends to settle at right angles to the magnet. That's swinging around. You've got to get all the twist out of it. But it settles like that, straight on, because that's the most repulsive, if that's the right word, way to get it. The ends, they can say I'm repelling the end there, much like the roundabout. That's diamagnetism and paramagnetism. We tend to use ferromagnetism in school, don't we? But there's more to magnetism than iron and steel and nickel. Right, we've done that one. Okay, I had a lovely session last night with some little brownies in the village, and we did this experiment. I just want to show you this so that you get some ideas of what you can do. You must have seen me do this before. Children are amazed that they can do this. This one, we have a placemat. That side's smooth, that side's a bit rough. Put the rough one off. A couple of tubes above. You can do it with as many as you want. And whatever you want to put on the tubes, there's an orange. There's a juggling ball, and if we knock the tubes, the bottom's smooth, so it slips off. The next layer is cork, so it's a little bit rough, so it moves the very light Smarty tubes out of the way, and the only forces left are the force of gravity, the force between the earth and the orange and ball, and it falls to the ground. I wonder what I'll hit if I do this. But it's very easy to do, and as long as the children don't dither, they get it right. One, try not to hit anything. 1, 2, 3. And they're in the thing. Easter time is coming, so you can do this with whatever you like. I'll just use one. Don't need to use Smarty tubes. Toilet roll. Well, we'd obviously use an Easter egg. You can't use ordinary eggs. If you're using a fresh egg, put some water in your beaker below. But again, we can smash this off. In every time, everyone a winner. Or you can even, do something even bigger, even more ambitious. Try Big egg, wow. We get in the box. Ready, steady. Oops. Ready, steady. Straight in the box. Wonderful. Example, inertia, whatever you like, forces and so on. We're back to Rute for the strength of eggs. Are you okay, Rute? Yes, she is. Wonderful lady.
Yes, but after this presentation, I'm afraid to disappoint. Amazing, David. Thank you for your energy. So I hope you can see. Well, I can take this. These are fresh eggs, and I hope I can have them in the end of the day for my dinner. So let's see if this is going to work. I'm going to put here a tray. I think it's a tray. And kids love this. They always want to try put lots of things here inside, because the question is how many books or how many things I can put inside of this tray. Do you think the egg will support all of this weight, like all of these books I have here? And the kids, oh no, it's impossible, miss, because for sure the eggs, they are so fragile. And I say to them, well, don't look to the eggs like they are fragile, because they are not. So just put some weight inside. Like, let me see what I have here. So I have a can, one. Maybe I can add another one. They are full, okay? And maybe, let me just, one book or two or three or four, and another one very heavy. And here I said to the kids, I told you that this was very heavy, but how do we know? So you always have to ask questions, because it's empty. So you have to measure, use a scale to be sure. So don't let anyone to fool you. So I told you that this was heavy, but I said to the kids, ask always, look if it's true. So, and I can put much more. So this is my physics books that I have here in my lab. I have more, but you can imagine that I can put much more, and the eggs will stay exactly the same. So they are not cooked for sure, they are fresh. Well, I could show you, but you know, I need them for my dinner. So why does this happen? So the eggs look so fragile, but they are not. They have this special shape that in Portuguese is catenaria. I think it's catenaria you call. So when we use a string like this, you know, we always have this shape, and this shape is amazing, because wherever you put the forces here, in any point of this curve, the force is divided in an equal way. I think it's something like this. Sorry, my English. So we also can do this with only one egg. Of course, we can do with only one egg. With one egg is more difficult to balance, but we also can do. I can try now. Yeah, and maybe try with another one. I don't know. Yeah, it's not so easy, but you can see the egg is exactly in the same way. And then with just a simple touch here on the table, you know that the egg will broken. So we also can talk about the shapes of some buildings. We can talk about architecture and so many things with this experiment. Thank you. Pass to you, David.
The other thing you can use for your eggs is tape, little rolls of tape, sellotape we call them in England. the little round insides and one egg in the top, one tape on the top, one on the bottom, and it gives the egg a little bit more stability. You get more stability, of course, in the egg box. So the one I like to do with that is using a tree trunk. This is 10 kilograms. Oh, and as long as you rest it very gently on the eggs, it holds the eggs, right? And then the next thing to do, which is on the next video, and this is something else, another story, this is an inertia, is to bash the nail in. Here you go. Here we are with a hammer and a nail, 10 kilograms worth of wood and 18 eggs below. Are you ready? Will they smash up, do you think? Will I have scrambled egg for breakfast? Let's get this going. My goodness, no effect on the eggs at all. And that's because not just the eggs are strong, but because of inertia, isn't it? The inertia, the big mass of the wood enables me to knock that nail right in. So there we are, another example on the strength of eggs. Quite amazing. And I think as well, the boxes are made as well to sort of enable the eggs to support things just as much as anything else. But of course, really that experiment is about the strength of the eggs when you put it on, but inertia when you hammer them in. Have a nice day. Right, okay, so in fact that's the end of really what we've prepared. And there's one or two other things. Just must share this with you because I found this on the internet the other day this week, in fact. You know the experiment with the bottle where you have a bottle upside down and you put a note underneath and you say if you can get the note, well, you don't give the note away, but how do you get it out? And there's two standard ways to remove the note. You mustn't pull it upwards because that tips the bottle. And watch this fail, but if you pull it down slightly, 1, 2, 3, and chop it, just about, got it out, let's try again, 1, 2, 3, let we get it out. Or the other way that is often in the books is to roll the note and just push the bottle gently off. Analyze that with regard to the size of forces and so on. But here's another way. And this is, to me, is really cool. I'll just put it that way just so that I'm going to be sure that it's not going to fall. One finger. You're only allowed one finger. How do you get it out? Nothing happens. Nothing happens. Well, that's the only way you can do it. Ah, there's another way. Look, watch. Wet finger. Dare I say that's magic? No, it's science you don't see. The extra friction of the water, which is interesting because when you do the lifting experiment like that and analyze the forces that are acting there, you don't want a wet finger because the wet finger slips off the glass. The wet finger gives you more friction on the paper. Wowie! I think we've done quite well there. I think we've done several experiments. I hope there's been some new ones for you. Oh, there's this one as well. I was going to show you this. You know, this old one here where we drop usually keys and you say what happens next when we drop. This is a massive mug. And we drop the, we've got a little man here, we drop it, let's see, 1, 2, 3. The string, that's what held it, didn't fall. The string wraps around and there's enough friction there built up to hold the moment of inertia and so on. As it gets closer, the little man goes faster. But this is an interesting one. So if we take a piece of string and, well, let's be good, we'll use a Science on Stage pencil. You could use a nail, you can use a wooden spoon handle. So we've got one tin here, and we wrap the string around the pencil. How many wraps? Well, I'll tell you, it's 5 or 6 invariably will hold it. 1, 2, 3, 4, 5. Oops, 5. See, they need the 6th one. 6. Nothing on the end. 6 is holding a can. Now, here's another can. How many wraps round will we need to get us to hold 2 lots of cans? Let's just take that off. Put the next can in the bag. So now we've got twice as much weight pulling down on the string. Right? You can see that? 2 cans. Well, we had 6, so we definitely will need 6, won't we? 1, 2, 3, 4, 5, 6. But that will surely slip now because there's twice as much weight. Still 6. So why is it still 6? There's tonight's question. Think about that in bed. Okay? And it'll be on Facebook eventually. And it's actually the next write-up that I've got in physics education. So there we go. Circular. Okay, so it's this hexagonal and square in the middle of circular. And the reason for that is that sideways on, it's not flat. But those are called ambiguous solids. Really interesting, especially if you've got a 3D printer. Good night all. Sleep well.